Continuing with your basic understanding of nanotechnology, as of now we have talked about the basic geometry as well as the classification of nanomaterial based on their chemical nature. Apart from it, we have talked about the three major synthesis route, including the physical route, the chemical route and the biological route, which is based on templates and using different kind of enzymes available from biological systems. Today we will be talking about the basic characterization of the nanomaterials. So, in terms of the characterization could be classified into two broad categories. One set of characterization includes the understanding the geometry of the nanoparticles. The other one includes understanding the surface properties of nanomaterial or surface chemical properties of nanomaterials. Okay. So, I will give you an overview of all the techniques, and based on that you should be able to judge, or you should be able to be in a position to decide what kind of technique you will be needing and what is the purpose that is going to solve by using that particular technique, or what is the question which could be answered by using that particular technique. So, coming to the slides where we started this. So, here when we started talking about nanotechnology, we decided that we will be talking about the classification of nanomaterial based on shapes and geometry, based on their chemical nature, having organic, inorganic or carbon based. Then we talked about the synthesis, where we talked about physical, chemical and biological basis, and here this is the segment what we are going to talk now, characterization of nanomaterials. Okay. Characterization of nanomaterials. Okay. So, as I mentioned, the characterization could be separated in two categories. One is characterizing the geometry, size, and also we can call it morphology. Whereas the other set of characterization includes your surface chemical properties, I use the word surface chemical because when we talk about nanomaterials, we talk of a dimension which is maybe 1 atom or 2 atom thick. So, it is almost the surface what you are studying. So, it is not a bulk. So, that is why I say the surface chemical properties and presence of different types of functional group. Okay. Apart from it, at times we do use, whenever we make thin films of nanomaterials or a layering of nanomaterial, we study their water interaction properties. So, we can put another category here, some of the physical properties. Okay. In terms of their interaction in polar and non-polar solvents. Okay. Now, when we talk about the geometry, size or morphology, we basically stress upon the microscopy techniques, and here we are no more in a position to use optical microscopy. So, we are entirely dependent on the electron microscopy. So, the electron microscopy tools what are being used for understanding the geometry, size or morphology includes transmission electron microscopy, scanning electron microscopy. So let's enumerate. So, you have transmission, electron microscopy, and sometime we go at a high resolution, in short you can call it TEM, high resolution TEM. Then you have scanning electron microscopy, which is SEM short. Then you have atomic force microscopy, AFM, and then you have scanning tunneling microscopy, which is called STM. These are the 4 different microscopy techniques which are being utilized to understand the geometry, size and morphology of different kind of nanomaterials. So, when you talk about transmission electron microscopy, to start off with, okay, so when you talk about TEM or high resolution TEM, HR, sometimes it is called HR TEM, high resolution TEM. So, say for example, this is your material, this is the geometry of the material which is there in front of you, and say these are nanoparticles, okay, and this is what you want to study in a high resolution TEM. So, what will happen, you will shoot the electron beam. So, when you shoot the electron beam, so if it gets obstructed here, some of the beams will move like this, some like this, like this, like this, and on the back you are having a on a plate where you are imaging it. What you are going to observe is wherever the electron won't be able to pass, you will see a shadow out there, and wherever the electron will pass, you will see a different kind of contrast, which I am showing in yellow. So, based on this, you should be able to figure out. So, you are having the particles. Now, I am showing in orange. So, you are having the particle, and you can see the dimension of the particle, and this is how the electron is getting transmitted, and this is what we call as transmission electron microscopy. So, you are allowing the electron to pass through those beams which are getting collided with the particles, is unable to reach to the plate, and that is where you see a contrast of on the screen. Okay. So, this is what you get from HRTEM image, and you really can go down to a resolution of 1 nanometer or less, and it is one powerful technique to study the particle size and the pattern of the arrangement. But what it doesn't do, those who do photography, they may realize it won't give you that three-dimensional feeling. It will come as a two-dimensional picture on a screen, because in order to get a three-dimensional feeling, you needed a slightly different way of throwing the beam on your sample. So when we talk about getting a three-dimensional view, we move on to the next technique, which is called scanning electron microscopy. So what do you do here? So out here you shoot the beam with a certain energy, okay, some X amount of energy with which electron volt you are shooting the beam. Now what do you do? So here again you are having a sample, same situation. So now we'll be talking about the second technique, which is your scanning electron microscopy. Okay. Out here, what you are going to do? So here is your sample. These are array of atoms sitting out there. And one more thing I forgot to mention is, when you do TEM, or transmission electron, depending on the kind of particle out here, you may even be able to see the surface of the particle with the electron density pattern, which we call as the fringe lines. You can observe this in the pictures. If you see a transmission electron microscopy picture, you will be able to see the fringe lines. So now coming back where I was on the scanning electron microscopy. So now here is your sample. Now you throw the beam in a way. Now your electron beam, you are throwing the beam in such a way, you are scanning through the substrate. You are not throwing the beam at a very high energy. You are throwing the electron beam at a lower energy, and what you see, the beam is scanning through the surface. Something like this. Say for example, I have to get a three-dimensional topography of the substrate. So something like this. So eventually what you are going to get is a very neat three-dimensional profile. So in the black I am doing the three-dimensional view of the substrate or the nanomaterial. So what you are going to get in a picture will be a much more three-dimensional view of the concerned nanomaterial. In other words, when we deal with scanning electron microscopy, we are getting a depth sense or sense of depth, or the z-axis. Here we mostly get the x and the y-axis in the TEM, whereas when we talk about a SEM, we get a sense of depth and the third axis. But when we do a SEM, where we are shooting the electron beam at a lower energy level, we lose upon some of the resolutions, and that's why the particle size determination using SEM at times can be a little tricky. So these two techniques, on one hand, when we talk about the SEM will give you a very good approximation of the size, really good approximation of the size and two-dimensional geometry. It will be perfect the way it is going to give you. Whereas when we talk about the SEM, we get a three-dimensional view of the particle. So you see, the techniques complement each other. They help each other to build up the story of things which cannot be seen so easily, cannot be seen through light microscopy, and that's where we say the different techniques complement each other to tell you a story which is never told before in the history of mankind. So, the next technique in the same line is called atomic force microscopy. So, this is again a very interesting bit of innovation of mankind. So, the way it works, so AFM. So, AFM is one beautiful surface characterization technique. So, say for example, I have a surface like this, drawing the surface, a pattern depth like this, or a surface like this. You could see the distinct feature of the two surfaces, or a surface like this. Now, what I do, I take a probe like this. Just imagine a probe which can really travel through it. So, this probe is traveling on the surface like this. It's tapping on the surface and it is moving, and this probe is a micro cantilever. It's something like this, and this tip is traveling like this, and based on its travel you start mapping the substrate. Or say for example, this tip is now traveling like this, and you can do it in multiple ways. I am just giving a very simplistic view of AFM, something like this. So, this could be done in two ways: you can keep it fixed or you can tap it. Okay. So, this is the third very powerful technique where you should be able to see another aspect which partly we observed using scanning electron microscopy is a three-dimensional aspect. Or say for example, if you see a picture of say graphene, which is essentially a 2D material, but at times you may have multiple layer of graphene stacked together. So, you should be able to see if you see a AFM picture, you will see a color profile telling you how many layers of graphene is stacked. So, that is the power of this technique. This technique can give you at times, are the particles aggregated? If they are aggregated, then it should be able to tell you that this is the kind of change in depth which is happening in a layer. So, it means these are multiple layers, and it is able to kind of scan through it very neatly, its probe. So, this is a cantilever based technique. You can call it a molecular cantilever based technique, which complement your scanning electron microscopy, transmission electron microscopy, and AFM. So, whenever you pick up any journal paper or any work you have to do, you have to realize that a reviewer is going to ask you that how the AFM picture looks, how the temp picture looks, how the SEM picture looks, and based on that they build up the story that how it is going to shape up, what kind of particle are we seeing, what is the nature of the particle, and how possibly the particle may be interacting. Okay. So, these are the three basic techniques, and the fourth one in the line is scanning tunneling microscopy, which I'll leave for you guys to explore, which is in the same line of atomic force. And if you look through scanning tunneling, you will be able to figure out what scanning tunneling microscopy is all about. I'll leave it for you guys as an assignment to see what is scanning tunneling microscopy, and from here we will move on to the physical properties, and physical properties, the techniques to understand the physical properties, and the surface chemical properties and presence of different functional groups. Thank you.